Welcome to the AI Research Roundup. I'm Alex. Today we're looking at a paper trending on X, published on March 1st, 2026, just 6 days ago. It introduces a breakthrough method for robots to achieve safe physical interaction by using only basic motor signals, completely bypassing the need for expensive force sensors or complex reinforcement learning. The paper is titled Minimalist Compliance Control, and as we'll explore in the upcoming figures, this plug-and-play approach delivers some really impressive accuracy, with significant implications for making advanced robotics far more affordable. Okay, Figure 1 breaks down the entire system. Panel A illustrates the core idea. Instead of using force sensors, the system estimates external forces directly from motor signals, using the robot's Jacobians, which relate joint movements to hand position. These estimates then drive a virtual spring mass damper to adjust the robot's movement. Next, Panel B highlights that this approach works across different robot bodies. Finally, Panel C demonstrates its plug-and-play nature, seamlessly integrating with high-level planners, like vision language models, for tasks like drawing or cooking. Well, Figure 2 dives into that plug-and-play capability, showing how different policies connect to the controller. The top sequence visualizes a vision language model pipeline, where tools like Gemini process stereo images into 3D contact points. Below that, 3 policy types are outlined. Row A shows a vision language model policy, outputting stiffness and force commands from text prompts. Row B demonstrates an imitation policy, relying on camera and internal sensor data to set desired positions. Finally, Row C outlines a model-based policy driven by target velocity. Across all 3, the Minimalist controller seamlessly translates these outputs into safe physical interactions. Alright, Figure 2 detailed the planner integration, so Figure 4 puts the controller to the test in a drawing task. The toddler bot attempts to trace a heart using a trajectory from a vision language model. The 3D graph on the left maps the robotic hand's movements across different control methods. On the right, the actual whiteboard results show that reinforcement learning baselines, like Uni-FP and Facet, struggle to maintain steady contact and distort the shape. By contrast, the full Minimalist method smoothly tracks the target to produce a clean heart, proving it handles delicate physical interactions effectively. Okay, we just saw the toddler bot successfully trace a heart without actual force sensors. Figure 3 validates exactly how accurately the method estimates those missing force readings. The top graph tracks the toddler bot, which uses servo motors with high gear ratios. The dashed lines representing estimated forces closely follow the solid ground truth lines from a physical sensor, achieving an error of under 1 Newton. The bottom graph then plots the ARX arm, which uses quasi-direct drive motors. Here too, the estimates and actual measurements align tightly, averaging just about 1 Newton of error. This proves basic motor signals provide highly reliable force estimates across different hardware. So, with the force estimates proven accurate, Table 1 puts the controller head-to-head against reinforcement learning baselines. It tracks position and orientation errors, alongside the humanoid's root pitch, which acts as a proxy for contact force. In the bottom row, the full Minimalist approach achieves a position error of just 16 millimeters. This significantly outperforms the Uni-FP baseline, which struggled with an error of 58 millimeters, proving that this streamlined classical control easily rivals complex learning models. Alright, after Table 1 proved the numerical superiority of this streamlined control, Figure 5 demonstrates it in action on the toddler bot. Panel A shows a vision language model guiding the robot on a whiteboard, where the baseline position control often loses contact or presses too hard. Panel B then features an imitation learning policy for a delicate egg placement task, achieving an 80% success rate, which cleanly doubles the baseline's performance. Finally, Panel C illustrates a model-based policy rotating a ball, proving that the Minimalist controller consistently maintains stable physical contact across completely different planning paradigms. Well, moving from the humanoid to dexterous manipulation, Figure 6 focuses on the leap hand. Panel A illustrates a vision language model policy for multi-finger drawing and wiping. The Minimalist controller successfully writes the letters OK and wipes the board, whereas the baselines fail by missing the board or pressing too hard. Panel B then demonstrates model-based planning for in-hand reorientation. Our compliance control smoothly rotates the items, while the standard position control simply drops them. This proves the approach perfectly generalizes to complex tasks demanding precise force regulation. Okay, stepping back, 2 main takeaways stand out. Minimalist compliance control achieves safe physical interaction using only built-in motor signals, completely bypassing expensive force sensors. This fundamentally lowers hardware costs, making advanced robotics much more accessible. That's it for this episode of the AI Research Roundup. I'm Alex. Thanks for listening.